Thanks again, Grzegorz.
Okay, well, it's just okay. Can you see it?
Yes, I can. I think everyone.
Okay, so hi everybody, and thanks for having me. So I mean, so I will, especially Grzegorz talk, it's very useful because he already set up many of the concepts. So I will be mainly concerned about going beyond mean field theories. So as Grzegorz mentioned, let me say that what I call first principle mean field theories, like mode coupling theory, but also spin glasses with paresis, one step of RSB of replica symmetry breaking, and also liquid in infinite dimension, they all share this nice behavior of the correlation, which is observed in actual supercooled liquids. The fact that you have this double step relaxation, and you can identify these two regimes, the beta regimes where you stay close to this plateau value, and the alpha regime where you exit it. And the beta regime corresponds somehow to the caging that as we can imagine in actual space in a supercooled liquid. And the problem is that, as Grzegorz mentioned, is that in all these theories we have a kind of we have an actual transition, a sharp transition where the two time scale diverge, and it also that is also accompanied by a divergence of fluctuations and of the correlation length. And as Grzegorz already mentioned, this transition does not occur in practice. So I will be mainly concerned about how to remove remove this transition and see that it becomes an avoided transition, so that we can extend somehow the prediction and the picture that we have from this theory, which is so nice in many respects, how we can extend it below TMCT. And the idea is that essentially, in order to remove the theory, one has to consider to remove the transition, one has to consider fluctuations that transform the sharp transition into a crossover. Okay, the idea I mean, in order to build a theory to describe this phenomenon, the main assumption is that fluctuations are small in the beta regime, and the correlation length, the dynamical correlation length in the plateau, so in the beta regime, is large. So in this sense, this implies that a coarse-grained description in this region of times should be appropriate. And one can show that okay, there are academic models. I will discuss. I will show this at the end of the talk, when this assumption can be shown to be true, but it is essentially an hypothesis for actual supercooled liquids. And how this this hypothesis, we can use it in order to assume that since the correlation length is large and these fluctuations are small, the problem in the beta regime can be described by a coarse-grained theory. And then this leads us to universality, because the idea is that different microscopic models may display the same phenomenology if they are described by the same effective theory at a coarse-grained level. So the idea is that the same theory could apply to supercooled liquids or also 1 RSB spin glasses. Okay, so independent of the microscopic of the model, and also again, as you can imagine, this is a kind of mesoscopic theory with some parameters that are free and that should be fixed coming from the microscopic. So, and this is an open question. I will be back on it later. So anyway, by using kind of symmetry arguments and so on, you can somehow devise how this theory should look like, and then okay, you end up with something a little bit technical, but you end up with an object that instead is rather intuitive. And the important thing is that with this object, with these equations that I call stochastic beta relaxation equations, you obtain that the sharp mean field transition becomes a crossover. The validity of such a theory for an actual supercooled liquid could not be assessed from within the theory, okay? Because I have already made those assumptions, so that the correlation length is large enough. But again, this kind of assumption could be tested numerically, and we already know that typically dynamical correlation lengths in supercooled liquids are not divergent, definitively not divergent, but still they are pretty huge. So it is possible, it is at least, I mean, worth of investigation, the fact that beyond the universality that we see in many phenomena associated to glasses and supercooled liquids, is the fact that there is a kind of effective theory governing some of those properties, and this is due to the fact that those systems develop a large correlation length, although not infinite. Okay, so now I will introduce essentially this stochastic beta relaxation, and I will show you its qualitative properties. So the theory, the object of the theory, it's this function g of t that describes the deviations from the plateau value of the beta relaxation. Okay, so and within MCT, but also within the infinite dimensional limit of the dynamics that Grzegorz were discussing, and also within spin glasses, we know that in the region, in the beta regime, this g of t is described by this general equation that is that already has many features of universality, because it also for many different models. And as you can see, it is a quadratic equation. So okay, so because essentially it describes a small deviation, the region close to the plateau value. In this equation, the parameters of the model are essentially controlled by this sigma, the separation parameter in Goethe terminology. And when when this is 0, we are at the MCT transition temperature. When this is positive, we are in the glassy phase, so this correlation no longer decays, while when this is negative, we are in the liquid phase, and this g of t at large time will become very large, meaning that we will be leaving the plateau. Now, stochastic beta relaxation essentially starts from these equations and promotes this g of t, which is at the mean field level, if you want, it's the same on all points, on all the region of the liquid. It promotes it to a field. So now this g of x, g of t is replaced by a g of x and t, and this time part with the memory kernel, it's essentially the same. Then you have a gradient that couples different points in spaces and makes somehow for a smooth profile. But the key point is that this term here, this s of x here, is a kind of local variation, it's local deviation of the temperature, if you want, from the mean field value. And this s of x is Gaussian distributed and is essentially delta correlated in space. So if you want, stochastic beta relaxation is a mean field theory, because it has the same structure of a mean field theory with quenched fluctuation of the temperature and or the density, if that is your order parameters. So the first thing that you get from the solution now, these equations, I mean, you can analyze it in some regime, but if you want to study it in finite dimension, you have to plug them, to put them on a computer, and what you see is that, as you can also expect, the first thing is that the glassy phase that is predicted by mode coupling theory for a positive value of sigma disappear. And the reason is essentially that even if this sigma is positive, so you would be in the glassy phase, this S of x is Gaussian distributed. So there will be always region where this sigma plus S of x, the actual temperature, local temperature of the system, corresponds to the liquid phase. And so this will drive you, due to this gradient term, this will eventually drives the system out of the plateau. So the equation already account for a disappearance of the sharp transition, and that becomes an avoided transition. But you can also understand within this equation why you have also a kind of crossover. So let me show you in this case the black line, the black continuous line is the solution, is the prediction by stochastic beta relaxation for the alpha relaxation time. So within MCT you would have a divergence here at sigma equal to 0, while instead stochastic beta relaxation removes the divergence, but it leads you to a pronounced increase a much more pronounced increase of the relaxation time. So, and it accounts essentially for fragility, and indeed it can fit very nicely the behavior of the alpha relaxation time for a fragile liquid. So you can understand this different behavior because in this region, while in this region the liquid behavior is the typical behavior of the whole system, in this region there will be rare regions that are actually liquid. And so since as we increase, if I go back to the equation, the fact that when this is positive and it becomes larger and larger, you need to probe the tails of the Gaussian distribution of these random fluctuations in order to get a negative value of this of the actual temperature. And this of probing the tails of the Gaussian Gaussian leads to this to the fact that these regions becomes extremely rare, and so you have a pronounced increase of the relaxation time. And if you solve the equation, you can also visualize this feature in real space. So here what I'm showing is the solution of the equation, and if you want now in this plot the peaks. We are plotting essentially the mobility, the local mobility. So and this is real space for a 3D system. It's a slice of the system, and the peaks corresponds to regions in this plane that are moving faster than the average, while the valleys corresponds to regions that are moving slower than the average. So the first thing that you may notice is that at sigma equal to 0, that would be the critical temperature of MCT, you don't have, I mean, the system is still relaxing, and you don't have, it is not frozen. But what is interesting is to look at what happens when you decrease the temperature and you go in the would-be glassy phase, and you see that the picture changes completely because while here you have a kind of homogeneous situation with fluctuations that were not too large, here you have very rare region where you have these large peaks of the the relaxation. And this corresponds exactly to the fact that you have these rare, very rare regions that have these liquid kind of behavior in a sea that is essentially frozen. And of course, this is resembling it is a nice visualization of dynamical heterogeneity as it is described, as it is understood from actual experiments. And you can turn this into a more precise result by comparing the diffusivity with the alpha relaxation time or its inverse. And so you have this again. So and then you see this Stokes-Einstein relation violation. So at small values, this dot here correspond essentially to the MCT transition temperature. So above the MCT transition temperature, you have the Stokes-Einstein relationship, while below stochastic beta relaxation leads to these deviations. Okay, so these are essentially the qualitative properties of the theory, and and these qualitative properties has been used in these plots to fit data. And as you can see, they fit data nicely, but still there are, of course, many parameters that have been tuned. Not so many, but there are some parameters that have been tuned. Now, what I want to discuss is that, in principle, stochastic beta relaxation, if you have a way to compute its parameters that are essentially coming back to the equation, that are essentially the value of sigma, or rather the connection of sigma with the temperature, but also the amounts of the fluctuation of the temperature, that is this delta of sigma. And then you have this parameter lambda, which come from that you can read in most cases from MCT. But so if you are able to extract these parameters from a kind of first principle computation, even a mean field computation, then you can turn all of this from just a qualitative theory to a more quantitative description. And this is what we have been doing, studying. So I will present you in the following. I will show you the validity of stochastic beta relaxation quantitatively in a kinetically constrained glass model. So, okay, so the kinetically constrained model that we have considered is a Fredriksson-Andersen model. So essentially, it's a spin. It's a system of independent spin on a lattice with a constraint dynamics. And the interesting thing is that you can put this model on any lattice that you want. And the key thing is that if you put it on a Bethe lattice, due to the local structure of the lattice, this model, the Fredriksson-Andersen model, display a sharp dynamical transition with all the feature of a mode coupling theory transition. On the other hand, this is a mean field artifact. In 2 and 3 dimensions, the Fredriksson-Andersen model does not have a transition. So let me show you some simulations here. So on the Bethe lattice, the model display this two-step relaxation, and you can analyze the behavior close to the plateau, and it is really mode coupling theory like. While instead on the regular two-dimensional lattice, the model does not have a transition. You can see here that the temperature, the critical temperature, according to the Bethe lattice, that would be to the Bethe lattice result, that would be a kind of mean field theory of the 2D actual model. The critical temperature would be 0.48, while here you can reach 0.39 and you still observe a relaxation. So the problem is how to go from here to here. we don't know how to obtain quantitative prediction for this model. So what I will do essentially, I will consider a different model, I mean, the same Fredrickson-Anderson model, but on a different lattice. So this lattice has a very specific property. So it depends on a parameter, and you can tune this parameter so that when the parameter goes to infinity, you have essentially the better lattice result. But as soon as this parameter is finite, you have a finite dimensional lattice. So this lattice has the property that locally it looks like a mean field lattice, but on large distances, it is really a finite dimensional lattice. And so in the end, you will not see a sharp transition, but you will see a crossover. So this lattice is defined through this, what we call this M-layer construction. So essentially, the idea is that you start from your original lattice, you make M layers, M copies of the original lattice. So this parameter M is really the number of copies of the original lattice. And then you rewire somehow the links between the different layers, and in this way you end up with the lattice with the properties that I have mentioned. So when M is equal to infinity, the model is, this lattice is equivalent to a beta lattice, and you have a sharp transition. But whenever M is smaller, is finite, is not infinite, you have a finite dimensional system, and so you don't have a sharp transition, you expect a crossover. The interesting thing from our point of view is that you expect that when M is large enough, the crossover is precisely described by a coarse grain theory. So what I want to show is that if this is true, then this theory should be stochastic beta relaxation. And in that case, you can extract the quantitatively the parameters of the theory from the beta lattice solution. So let me show you the results. So the solid lines are simulations on this model, and we are sitting at the critical temperature of the beta lattice of the model, so 0.48. And you see so that when M goes to infinity, indeed, this G of t is the deviation, is defined as the deviation from the plateau value. And so when M goes to infinity, you are on the beta lattice, and you don't, and you never escape the plateau. This will approach with the power law the plateau value. But as soon as M is finite, you deviate, and even if you are sitting at the critical temperature of the mean field critical temperature, you actually escape from the plateau. The point is that these dashed lines here is what is obtained from the theory, okay? And the thing is that, and these are parameter-free predictions in the sense that the numbers that are put into the stochastic beta relaxation equation are obtained from the mean field solution, from the beta lattice solution. And okay, and so this is the only instance that I know of a model where you can get quantitative predictions beyond mean field. Of course, at the price of having a kind of academic model, no? Because anyway, the Fredrickson-Anderson model is already academic, but then you apply this construction. But anyway, what we were interested in here, it was to show that when stochastic beta relaxation is expected to work, then it actually works. And the theory, it also allows you to study fluctuation. So here it also gives you the chi4, and here what I'm as you can see now, the data are at the points, and the theory the theory is the solid line, and as you can see, the chi4 should diverge, should increase indefinitely as the system approach the plateau value at the mean field level. while when you start to deviate from the mean field behavior, these deviations are well described by the theory. And so this is essentially all I wanted to say. So I started by discussing why we need to go beyond mean field theory. I presented you stochastic beta relaxation and those equations and their properties according to the solution. And then I wanted to show, and then I wanted to show you that it actually works in a non-trivial finite dimensional model where the transition is actually avoided. So I think I will stop now, and okay, and then okay, I will just make a comment about the fact that, as I mentioned, these parameters here that for the simulation that I've shown could be computed from the actual theory, from the better solution of the problem. One would be interested if the theory is supposed to work for an actual finite dimensional supercooled liquid to extract these parameters. And these in principle could be extracted from MCT, but one should need at least to extract this object here. So all to say that it would be important to have a prediction for the fluctuations for the chi4 in the context of MCT, because those predictions could be used to go beyond the MCT temperature. So that's all I wanted to say, and I thank you for the attention.
Thank you very much, Tommaso, for your very nice and interesting talk. Are there any questions from the audience? Let me see. Grzegorz?
That was a great talk, Tommaso. So what the question that I have had from the very beginning when I heard for the first time about this theory, I read your preprint before the Barcelona conference, if you recall, and then you talked about it in Barcelona. Your noise is a static noise. Is this because you are close to the plateau? If you were to extend this into the alpha regime, would the noise still be static noise, or would it be correlated in time?
Okay. Yeah, indeed, it is. That's a very interesting. I mean, it's a crucial point indeed. The thing is that, okay, the noise, it appears to be quenched, and this is only true. I mean, this happens because you are working close to the beta regime. So it is an outcome of the computation, and on the same time, it reminds you that you are doing a computation assuming that you are in the beta regime. And so these assumptions must break down at some point when you leave the beta regime. And so this tells you two things. First, that the alpha regime still needs to be done, essentially. And on the other hand, that indeed this is really a theory of the. And on the other hand, the nice thing is that it's telling you is that somehow when you are in the beta regime, there are some degrees of freedom that are actually frozen. I mean, that there is something that really looks like it is frozen. So. And this is what allows you to define dynamical heterogeneities in the first place, because it tells you that if you take a snapshot of the dynamics, there are regions that moves faster than the other, but then you know that in the end, everything must be ergodic. So those regions at some point, later in time, should become blocked region, and other regions should become activated, active regions. So this is all an open problem of the theory.